Hi, my name's Nick Skinner. I'm a researcher at the Mount Sinai Light and Health Research Center located in Menands, New York. I'd like to thank you for your interest in our plant health research. And today we're going to be discussing a project that we conducted which sought to look at the use of germicidal UVC to control cucurbit downy mildew. UV treatment has shown promise for treating various disease and crop combinations. It's particularly effective at treating powdery mildew in strawberries. It's shown promise for treating powdery mildew in grapes, squash, even cut flowers. We're participating in ongoing trials for the treatment of Cercospora leaf spot in beets. We've done research looking at powdery mildew control on cucumbers in the lab, as well as downy mildew on basil in the lab. One recurring theme that you'll see throughout this presentation is that our UV treatments are administered at night. The reason for that is that treatments followed by a period of darkness tend to be more effective than those administered during light hours. The reason for this is explained by the following. UV tends to damage the DNA of the pathogen, and many of these pathogens, like the majority of organisms, possess a mechanism by which they can repair their own DNA, and this mechanism is activated by the short wavelengths in visible light. So by treating at nighttime when these short wavelengths are not present, the UV dose is much more effective. Here's our villain of the day, cucurbit downy mildew. This downy mildew, which is a fungal disease, can infect various cucurbit vine crops, melon, squash, pumpkin, and cucumber. But of all these, cucumber is particularly susceptible. So this research seeks to determine whether or not UVC, germicidal UV, can be an effective control. So to test the efficacy of UVC against downy mildew, we conducted a dose and frequency exploration study. The UV doses that we tried were 120, 240, and 480 joules per square meter. Again, these doses were all administered after sunset. Dose frequencies were once and twice a week for all of those dose levels, and these combinations were applied on standard black mulch as well as UV reflective mulch. The table in the upper right-hand corner shows the different mulch types and what their reflectances are at UVC, which is 254 nanometers, as well as 436 nanometers, which is the short end of the visible spectrum. You can see the reflective mulch does a good job reflecting both UV and visible light, whereas the black does a good job of absorbing both of those. In addition to the UV conditions, we also had a conventional fungicide control, which was applied weekly for downy and powdery mildew, and was applied to the black mulch only. Additionally, we had untreated controls within both the black and silver mulch plots. The outcome measure we had was the percent foliar disease severity for downy mildew. These data were collected for the individual condition plots as a whole. Our cucumber variety was Raider, which is not resistant to downy or powdery mildew. It has intermediate resistance to angular leaf spot as well as to cucumber mosaic virus, and it's shown to have scab resistance. So in the next few slides, we'll discuss how we actually applied the UV. In order to do this, we designed and fabricated a custom tractor attachment. It was designed to fit a Category 2 3-point hitch. It had an onboard generator to power the UV sources, and had a remote switch box, which was located at the tractor operator station, whereby the UV sources could be turned on and off easily. Here's another view of the UV attachment, and in the underside you can see the lights which produce the UV. These are basically very similar to fluorescent high bay fixtures, but instead of using visible light sources, they use special Philips UV lamps, which are rated at 75 watts apiece. Now, each fixture used 4 of these for a fixture total of 300 watts. And the other special thing about these fixtures is that they had a special UV ballast designed to operate these lamps at their full power. You can see on the back side here of the attachment that there are curtains. And the purpose of the curtains, they have a reflective coating on the inside. The purpose is twofold. One is to provide a safety barrier for both the tractor operator and bystanders to prevent stray UV from exposing them, but also they serve to redirect UV back into the enclosure where it can be put to use. In this particular unit, we had an onboard 2200 watt inverter generator, which was nice and compact and readily powered the array without any trouble. Again, I mentioned earlier the operator of the tractor had a switch at his station where he could turn the light sources on and off. Because the output of these types of fixtures is essentially fixed at one level, you vary the dose given by varying your speed. And in the photo in the right here, we're actually calibrating the speed to give a particular dose, which turned out to be about 1.25 miles per hour for a 240 joule dose. The 2020 field trial was conducted at a commercial fruit and vegetable farm in southeast Massachusetts. The lower left of the slide shows an aerial view, and the field in which the study was conducted is shown with the orange box. You can see in the photo there's no appreciable shading, and the field received sunlight from morning till evening hours. The map of the various combinations of dose and frequency and mulch is shown on the right. Disease assessments were performed on 6 different occasions throughout the life of the planting and were performed by UMass Extension staff. Okay, so let's get into the results from the 2020 field trial. You'll see 2 disease progress curves here. The one on the left was for the conditions on black mulch. The one on the right were for the conditions on reflective mulch. The way to read this legend, you'll see a number followed by another number. For example, 120-1. That means 120 joules per square meter applied once per week. -2 would be 120 applied twice per week, and so on. You'll also note that there's only a fungicide curve for the black mulch. That's because we did not apply any fungicide to any of the reflective mulch beds in this particular year. So you'll note from both of these graphs that the untreated control, that's sort of like the darkish red line, fared the worst. And that's not unexpected at all, that if you had no intervention, disease would be expected to be the worst. That seems to be consistent in both. You'll also note here that many of the UV conditions perform very similar to each other for a given mulch. They're all clustered pretty close together. You can see that the fungicide did way better at controlling the disease than any of the other treatments. And another feature to take note of is that the disease progress curve for the reflected mulch seems to be shifted to the right a bit when compared to the black mulch, meaning that the reflective mulch for this year delayed the onset of the disease. Here we see another metric for looking at these data called area under the disease progress stairs. This is a metric which allows you to look at both disease severity and duration together in one figure of merit. So it readily allows you to compare the various conditions more easily. So here you can clearly see the fungicide only was the big winner. And you can also see that systematic difference showing up here between the reflective and black mulch. Also worthy of note, for a given mulch type, there wasn't an awful lot of difference between the various UV doses. So again, that's consistent with the disease progress curves. Here in our second year of field trials, the 21 trial, we look to compare UV, conventional treatments, and also combinations of them. So conventional treatment, again, was applied weekly with materials to control both powdery and downy mildew. We had UV only in some plots, and then we had what I'm going to call combination conditions, one where we put a once per week conventional treatment on top of the UV, and then another set where we had UV plus conventional treatment every other week. We put this one in to determine whether or not UV would provide enough control that you could reduce the number of conventional fungicide applications you would have to do, both to save you time and also some inputs. So all these treatments were replicated both on black and reflective mulch. We also had an untreated control, small untreated control plot on black mulch only. But we had 8 full rows of both black and reflective mulch that we duplicated all these on. All the UV conditions were 480 joules per square meter twice per week, again applied after sunset. The reason we went with this combination, even though in the prior year we hadn't seen an awful lot of difference between the different dose and frequency combinations, we thought that the higher dose and the more frequent application would give us the most likely chance of seeing control. So we went with those. Again, we used the same cucumber variety, which is Raider, and used the outcome measure of foliar disease severity. In this slide, you can see the aerial view of the field used for the study. Again, this was on the same farm as the previous year. One difference here, though, is there was partial tree shading in the afternoon and morning hours. This photo was taken probably earlier in the spring than the trial actually took place. So the shading that you're seeing here was more severe than what we were seeing during the trial because the angle of the sun was lower in the sky. I have a photo in the next slide which you can actually see an example of some of the shading that we did see. But the plot map is here on the right. You can see we had both black and reflective mulch blocks with the various conditions distributed in them. Here's a couple photos from this field trial site. On the left, this was taken in early July when the beds had been made but not yet planted. This photo was taken as part of our dose calibration procedure. And on the right, this was taken about mid-August, and you can see things were well underway. In that lower right-hand corner, you can see some of that end-of-day shading that I was mentioning earlier. So the disease assessments we did here, because our rows were a bit longer than we had in the previous year, we divided the rows into 10-foot segments. 10 total, we had 100-foot long rows. So samples were taken within a 2 square foot area within each of those 10-foot blocks. And then those numbers were averaged together to get an average for each row. Disease assessments were performed by a farm employee who was trained by extension specialists to scout for the downy mildew and other diseases. And disease scouting happened 5 different times throughout the life of this planting. So here we can see some of the results from this field trial. Again, on the left, we have the black mulch conditions presented, and on the right, we have the reflective mulch. Again, there was just one small plot of non-treated control. That was only on black mulch, so it'll only appear on the left side here. But as you would expect, that was the worst condition. Followed by UV did the next best, and then UV plus every other week of conventional application made some additional difference. And then conventional fungicide did slightly better than that, and slightly better than that even was UV plus conventional, the full conventional program. On the right hand side, you can see very similar trends where UV was the least effective. UV plus every other week conventional was slightly more effective than that. And then the fungicide plus the UV as well as straight fungicide also did very well and very similar to each other. UV plus every other week conventional, UV plus conventional, and conventional only were all significantly better than no treatment at all. And also interesting from this year's trial was that there was no significant effect of mulch that we had seen in the prior years. Here's another look at the data after going through the area under disease progress stairs calculations. And here you can see the relative gain of effect as you go through the various conditions. UV only for our statistical analysis did not show that it was reliably different than the untreated condition, even though when you looked at the plot on the previous page, you could see there was a difference in magnitude. You can see that same difference in magnitude here, but it wasn't reliable. That could be in part due to the fact that we only had one small plot of untreated control, but regardless, we weren't able to show a statistical difference. And again, there was no statistical effect of mulch overall. It is worth noting, though, that for the fungicide condition, that the fungicide conditions applied on reflective mulch seemed to fare better than those applied on the traditional black mulch. So at this point, I'd like to discuss some of our conclusions that we gained from this research. First and foremost, it didn't seem like the UV doses that we explored in this study were adequate to control downy mildew alone. And we also didn't observe any trends as far as increasing dose and getting better control, at least up to the 480 joules per square meter that we did treat with. There didn't seem to be any negative impact on plant health or yield observed in the UV treated conditions versus the ones that were not treated with UV, which suggests that the plants might be able to tolerate higher doses, which might help to also control the downy mildew better. Also, if downy mildew resistant cultivars had been used, they might have responded better. With regard to the combination approaches, the addition of the UV to the conventional program did seem to offer additional protection. If you were in a situation where you had extremely high disease pressure and you wanted to keep it from getting a foothold, this might be an effective tool. UV plus the reduced conventional applications, they did show a difference. But they didn't perform as well as the full conventional program. But because they did show a difference, perhaps it would be possible to find a combination of a reduced rate of conventional application plus the UV, which would provide satisfactory control. Maybe you could do something like going down to a 10-day spray interval instead of a 7-day. Also, another possibility would be the reduction of the amount of powdery mildew targeting materials in your spray if UV is used. Now, this is not something we particularly investigated in this study, but we have seen evidence from the lab that UV is very good at controlling powdery mildew in cucumber. It's also very good in other crops in the fields. It's also worthy of note that in the trials, although we weren't specifically testing this, it was noted that there was very good control of powdery mildew even in the plots that didn't receive any fungicide. So it's likely you might be able to reduce the amount of powdery mildew materials used, possibly saving some money that way. Now let's talk about the UV reflective mulch. Recall that in year 1, it was shown to have a significant effect, but not in year 2. One of the biggest differences between year 1 and year 2 was that the plot in year 1 had full day sunlight, whereas the plot in year 2 received shading in the morning and evening hours. How this might be significant is possibly one of two ways or a combination of both, maybe. Natural sunlight contains both UVA and B, which do in their own right have an effect at neutralizing the downy mildew spores. So it's possible that there's more sunlight and more UV being reflected into the underside of the canopy. And another hypothesis too is that the dark black mulch in the sustained sunlight produced heat stress in the plants, weakening them and making them more susceptible to infection. This would be in year 1 and not as much in year 2. So it could be a combination of these two effects. We're not really sure. Another important consideration is timing of the UV treatment. Now, you've heard me say that the treatment should be done when there's going to be a period of darkness following so that the DNA repair mechanism can be defeated. But also it's important to consider that new spores are also produced at night, and if you treat too soon, you'll miss those. You'll treat before they're produced and possibly not inactivate them. So the ideal time would be after the spores are produced, but before it's too late to defeat the blue light repair mechanism. Another consideration as to why UV effectiveness might be limited on downy mildew is spore pigmentation. Research has shown that the more densely pigmented spores are, the more resistant they are both to solar and UVC radiation. And as you recall, downy mildew spores tend to be fairly darkly pigmented, at least when compared to powdery mildew spores. So that may be a possible explanation as to why UV had limited efficacy. Another important topic I wanted to touch on is UV safety. Obviously, we call it germicidal UV radiation for a reason. We know it's harmful to bacteria and viruses and spores and all sorts of pathogens, but it can also do damage to your skin and to your eyes. But it can be safely applied as long as you follow some simple rules. And those are basically, one, that you should always prevent your eyes from being exposed to UV. This can be accomplished very easily by wearing a polycarbonate face shield or wraparound safety glasses made of polycarbonate when you might be possibly exposed to the UV. And the other rule is to cover your skin. If UV doesn't readily penetrate most clothing or things like that, so as long as you cover your skin, cover your eyes and face, you should be just fine. It's also worthy to note that tractor cab glass does not transmit UVC, and accordingly it will protect the occupants of the cab. So if you're using a cab tractor, you're in good shape. If you're using an open station tractor or you're using a cab tractor and you need to get out while the UV is powered up for whatever reason, basically just make sure that your reflective curtains are in good condition and are attached, and that you're protecting your eyes and covering your skin. So if you follow these basic rules, you shouldn't have any problems at all safely applying the UV. Finally, here I wanted to touch a little bit on UV technology advancements that have happened in the past couple of years. The UV attachment that we used for this particular study was based on tubular low pressure discharge lamps, which are very similar to fluorescent lamps. UVC technology for LED sources has been rapidly developing in the last couple of years. We're now to a point where you can match the power density of the low pressure discharge lamps with LEDs, meaning you can produce something with the same surface area and it will produce the same amount of UV output. And that's pretty exciting because you couldn't say that a few years ago. UV LEDs, as they develop, can allow for much more flexible equipment design. They're much more compact sources. They're more robust, less damage sensitive, and so on. You can design more specialty equipment, or multi-row units become more practical because the sources are a lot thinner. There's a lot of neat possibilities. Also, the output is less affected by the environment. Temperature tends to affect the output of the low pressure discharge type sources. So that wouldn't be as much a concern for LEDs. Also, as the efficiency improves over the coming years, designs can be actually much more powerful for a given size or footprint, which means you can achieve higher doses more readily, or for a given dose, you can increase your speed, which would translate to a much more economical treatment. Finally here, the dollar per watt figure is expected to be equivalent to the low pressure discharge sources by 2025, and then from there it's only going to get better. And that's really good news because it will further improve the cost effectiveness of this technology and reduce the startup costs for somebody interested in pursuing this. Finally, we would like to acknowledge the support of the Northeast SARE program, who funded this research, the contributions of our colleagues at UMass Extension, Cornell University, and Ward's Berry Farm. And last but not least, we'd also like to thank you, the viewer, for taking the time to learn more about our research and watching this presentation. If you'd like to learn more about what we do at the Light and Health Research Center, or to look up our contact information, check out our website. The address is shown here on your screen, and we look forward to hearing from you. Thanks again.